Hello, everyone, and welcome to today's webinar, Smart Chart webinar series focused on GDMS. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Xinwei Wang, Project Manager at EAG Laboratories.
Hello, everyone. This is a continuation of EAG's Smart Chart webinar. Today, we will be discussing glow discharge mass spectroscopy, a technique that redefines high purity analysis. I have over 20 years experience in material science and engineering, and I joined the EAG a decade ago, focused on purity analysis and material characterization, specialized in purity-related applications and problem solving using trace analysis techniques, including GDMS, ICP-OES, ICP-MS, IGA, TGIR-MS, etc. Today, this lecture is outlined as following. First, we will have an introduction to EAG, and then the smart chart, the fundamentals of GDMS, the case studies, which including full survey impurity analysis of superalloys, full survey impurity analysis of graphite and other carbon forms, full survey impurity analysis of high purity alumina, electronic grade titanium, as well as depth-specific measurement of impurities in multi-layered structures. In the end, we will summarize the strengths and challenges of GDMS, as well as the complementary techniques goes with GDMS. So EAG Material Science is a global scientific service company established in 1978 with 16 laboratory and 5 business development locations in over 10 countries. We serve more than 4,000 clients worldwide. Our 600 plus highly educated employees, combined with leading state-of-the-art technology equipment set, enables us to leverage the power of science and engineering to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. We offer GDMS analysis in 3 locations global-wide, including Syracuse, New York, Toulouse, France, and Shanghai, China. Syracuse, New York is the center of excellence driving the technical development. The EAG Smart Chart, which is an acronym for spectroscopy and microscope analytical resolution tool, offers a concise visual reference tool for comparing techniques, permitting one to compare detection limits and analytical resolution for numerous material characterization techniques, evaluation of surface, purity survey, and more. Each bubble or bar represents a different analysis technique. Surface analysis techniques are represented inside the box, and the box techniques are represented outside the box to the right. These techniques have a very range of detection limits, but usually do not provide information regarding depths. But that's not always the case. Today, GDMS is the case. We'll show you that it also can do depth-specific information measurement. Imaging techniques are represented below the box. Below are the box or the imaging that the bubbles are color-coded and indicate the type of information each technique provides. The blue and the red bubbles show techniques that provide information on atomic composition and molecular bonding characteristics respectively. In this webinar, our focus will be on GDMS analytical tools. The technique can provide quantitative full survey trace analysis of trace impurities in bulk material, as well as depth-specific distribution information of impurities in engineering coatings and thin films. EAG has many depth profiling techniques. Each technique has different sampling depths. GDMS can provide hundreds of micron depths into a sample, making it an ideal tool for bulk measurement as well for engineering coatings. This slide gives you a glance overview of the purity service line in EAG. EAG has the largest commercial operation of GDMS contract service globally. This is led by Dr. Patira. EAG, we have 25 GDMS instruments to perform purity analysis of a majority of the material, but also have solution-based ICP-MS, ICP-OES, technique addressing other matrices. And we have IGA technique to provide gas-forming element information. We have thermal and microsampling technique and the sorption analysis for BET surface area and the pore size distribution analysis. Our GDMS technique is designed to drive technology innovation and to redefine high purity analysis. We have all the commercial GDMS instrument models from VG9000 to its replacement new Astrom in 2010. We also have fast flow GDMS, including Element GD and the Element GD Plus, which enables microsecond pulse sputtering for thin films and engineering coating analysis. Here are some drivers in material characterization needs. Number one is supply chain, including purity testing as well as purity certifications. Second category is technology advancement. This is particularly true in advanced manufacturing, additive manufacturing, high performance ceramics, engineering coatings, such as either environmental barrier coating, thermal barrier coatings that are put on high temperature alloys. Another driver is for the complexity of materials and the impact of impurity on material performance and reliability. And finally, regarding information and data paradigm. Client success requires control and optimization at all stages of the product life cycles. In EAG, we support from R&D, prototype, pilot, manufacturing transfer, reliability, and field failure analysis stages. We are positioned to provide knowledge and appropriate tools to help our clients achieve it better and faster. Give you an example here is that EAG certifies a very broad industry sector materials that requires high purity. As you can see here, we certified material for photovoltaic, fuel cell, sputtering targets, LED, high performance ceramics, semiconductor equipments, turbine, aircraft engines in aerospace, electronic materials, stands, and integrated circuits. All of those materials requires high purity, and many of them require tight control of specific set of impurities. In EAG, we not particular purity survey, we not only address the type issues with one technique, but GDMS is one important part to provide multidisciplinary analytic expertise to full product life cycles, including product innovation and improvement, investigation and troubleshooting, quality assurance, regulatory compliance, manufacturing and supply chain support, as well as consulting and litigation. So major application of GDMS, including lies in the fact that the glow discharge atomization and ionization process combined with a high mass resolution analyzer can provide bulk impurity concentration of inorganic solid samples. Specifically, it can provide quantitative measurement of trace and ultra trace level analytes in materials such as high purity metals, alloys, high purity carbon, graphites, semiconductor materials, oxides. And it is 7 elements full survey. It can establish traceability for unknowns from limited amount of samples. And it can also provide step-specific information. Here is a summary of the GDMS deliverables, including purity analysis that summarize all the elements from lithium to uranium, for bulk impurity concentration for depth-specific measurement, surface morphology, and surface contaminants information. Now we go to the GDMS fundamentals. Like any other techniques, it is in each measurement technique requires to deal with two important aspects: the precision and accuracy. Precision describes how well the measurement repeats itself. Accuracy describes how far off the measured values from the true value. There are four scenarios happens in any measurement. Number one is low accuracy and low precision. And then you have those with a good average accuracy but are not precise. The third scenario is where most measurements fall into is that they have good precision or reproducibility but are not accurate. With that, then we establish procedures and reference material to achieve both accuracy and precision. For trace analysis, direct solid sampling techniques are preferred because it provides easy sample pressure variation and low contamination risks. However, it is not coming without expense. In direct solid sampling technique, the matrix effect is a major source of measurement precision and accuracy. Since the signal intensity and the linear response range of the analyte can be sensitive to matrix composition, in mass spectroscopy, the challenges translates into managing the matrix effect or analyte ion yield. Here is the three scenarios. In the first case is the SIMS, which is using primary ion beam to spot a sample and collecting secondary ion yield. As you can imagine, because the ion signal is directly generated from the matrix itself, it generally shows strong matrix effect. In EAG, we're using thousands and thousands of standards to establish precision and accuracy. The second technique, spotter neutral mass spectroscopy, it collects both information of secondary ions and some neutrals. In this case, it exhibits modest matrix effect because there is atomization, ionization separations, and this allows part of the analyzed to be infinitely diluted in the plasma before it is analyzed. Now, what if we suppress the secondary ion yield and boost the neutral yield? We have GDMS here. This is a typical example where how matrix effect is minimized. It has a nearly complete atomization and ionization separation, so the analyte atoms signals are infinitely diluted in the plasma and before it's analyzed. From the analyzer's point of view, it means that it only sees the analyte atoms in the plasma and the chemistry memory of the matrix is completely gone. So this allows the GDMS to do quantification even when strict matrix matching standards are not available. Here is the more specific details of GDMS measurement principle. You have argon atoms are introduced into the GD source with the established electric field. It is started forming plasma, and this plasma argon ions will be accelerated toward the cathode, which is voltage negatively biased. And those argon ions will bombard the sample surface, causing its rejection out into the plasma, where it is ionized predominantly by the penning ionization process. So with those in mind, then the ions formed will be extracted to the high mass resolution analyzers such as magnetic sectors. The glow discharge source serves as a stable source for analyte ions with minimum influence of sample properties, including ionization potential, electric conductivity, etc., on any analytic characteristics. So one the important requirement for trace analysis is to have high resolution mass analyzers. Why? One of the main reasons is that the polyatomic species can form easily in the plasma. Give an example. In analyzing trace of iron in silicon, two mass interference to iron 56 happens. It's silicon diatom as well as argon 40 and oxygen 16. If we're using quadruple mass spec, we don't have really the resolution, and all those three are overlapping. So you will have forced to have elevated detection limits. Now, if we have mass resolution over 2500, we can separate those mass species, iron 56 from 28 silicon diatom as well from argon. With that, it enables us to do accurate, reliable multi-element analysis at the trace levels. How do you achieve it? Give example, here is VG9000 GDMS instrument. It has a ion generation source or GD cell, which is cooled in liquid nitrogen. This is served as a stable ion source. Once ion generated, it has different energy levels, kinetic energy, and mass charge ratios. So it needs to be extracted out and reshaping through the ion lens. And after that, it is filtered off with both magnetic field, electric field, which is achieved by magnets and electrostatic analyzers to achieve double focusing. After that ion is detected, we have dual detectors, photomultiplier tubing and flooded cape with automatic switching capabilities. GDMS has the ability to handle versatile samples, including chunks, powders, grains, fabrics, fibers, and blocks, through its coaxial sampling as well as flat sampling geometries. Quantification-wise, GDMS using ion beam ratio corrected by relativity sensitivity factors. For ions, of course, you are collecting ion current, so ion beam ratio using the matrix current as internal standards are established. This one is not a concentration yet, but using a relativity sensitive factor, which corresponding to the signal it can be generated per ppm atoms, you can generate the concentration of the analytes of interest. This ISF set has two important features. Number one, it is constant over a wide concentration range, and it has limited variation with the matrix composition. Here, give you more details with this generalized ISF set. Is that if you is in GDMS analysis, strict matrix matching is generally not required for quantification. If the letter series sensitivity factor of iron is set to 1, you can see that more than 50 elements having ISF set values between 0.5 to 2, with the rest of the 10-ish elements between 2 to 4. Okay. Thus, generalized ISF can be used by measuring single multi-element standard samples, and with that, we can do full survey analysis for even material without strict matching standards. The second type of element GDMS instrument we have is called element GD. It's based on fast flow GD source, and the ion generated through the ion optics and goes through magnet and the electrostatic analyzer. And the detector is different from the previous VG9000. Is that it has a Faraday and SEM dual detectors. Here is a blow-up of the fast flow source. You have argon sweeping through the sample surface and have the sputtering going on and the extracted ions going out to the ion optics. An important feature or important characteristic lies in the purified graphite source parts that are used to serving as anode cap, flow tube, and a mass extraction cone. The element GD has several important features. It is designed for rapid analysis of conductive solids. For bulk analysis, its sampling size is 8 millimeter, or represents roughly 50 millimeter per square millimeter, with sampling depths in hundreds of microns. Again, it has full elemental coverage, ultra trace level detection limits, very broad dynamic concentration range. Actually, it's more than 12 orders of magnitude. Again, it is based on ion beam ratio for quantification. One of the important features for element GD is that it can do effective depth profiling, almost completely free of molecular interference. Fast flow GD source can operate in two modes. One is continuous DC mode, The second one is post-DC mode. In post-DC mode, there is voltage rising, stabilizing, and off period. Two important features happens when GDMS is operating in the post mode. In the plasma quenching stage or afterglow stage, there is a population surge for argon metastables, which enhance penny ionizations. Second feature is that it will generate pressure waves during those pulses, which can affect ion transmission issues. Dr. Bob Hasterbeck in our facility has successfully addressed many of those ion transmission issues. Overall, operation in microsecond pulse DC mode can expand the analysis to low melting point metals and non-conductive materials. It improves depth resolution to tens of nanometers with a flatter sputtering crater bottom. It reduces thermal stress on sample. It enhances signal-noise ratio since most analyzed ions generated will increase penny ionization in the afterglow period. EAG does develop its proprietary GDMS softwares for a couple of reasons. We have a lot of instruments and different models and many GDMS staff. So a unified interface with traceability is important. Let's say who is doing it, on what instrument. So this user interface allows us to track the instrument collecting this spectrum and who is operating on it. Second important feature is that it does built-in mass interference calculation, and this color coding also shows the calculation is based on ASTM protocols or not. So next, we will present several case studies. We have GDMS and why it is used. Of course, it's used for industrial materials. So here, several case studies are demonstrated for high purity materials of industrial significance. In each of the case studies, we'll describe the material that are of interest and the roles of impurity played in those materials. And secondly, the analysis challenge of those materials and how GDMS addresses those challenges. And finally, the GDMS elemental coverage and the reporting limits for those materials. Case study number one is on full survey trace analysis of superalloys. Superalloys is used in a high temperature, high oxidation environment, so there are certain performance target. They are nickel-based alloys and need to achieve high tensile strength, high impact strength, high temperature creep resistance, high damage tolerance, and a long fatigue life. But pure nickel doesn't have those capabilities, so we need to start alloying to provide a mechanical strength with refractory metals such as titanium, tungsten, niobium, moly, rhenium, zirconium, hafnium, and many other elements in small amount. Because it is operating in the combustion environment, you need to provide oxidation and corrosion resistance. Hence, chrome and in part of aluminum will provide this oxidation protection. And we need to be operating reliably for long term, so other rare earth elements, as well as cobalt and zirconium, hafnium, rhenium will serve that functions. With each element is added, you run the risk of introducing impurities. And here shows the impurities. They are either low melting point phase forming elements, or they can form other impurities which were particularly harmful, including sulfur, selenium, tellurium, lead, and bismuth, even at sub-ppm levels. Give you an example, here is a US pattern, which clearly shows how clean superalloys need to be from tens or hundreds of ppm level about to less than 100 ppm elements, to less than 10 ppm elements, and to those ultra trace level elements. See how low it has to be controlled. In EAG, how do we do this? We start with a statistical process control our instrument using a nickel-based alloy, SRM346. We run the sample every day to ensure our instrument is within valid status of analysis. Here shows you the SPC chart of this alloy or standards. It covers element impurities concentration from less than 10 ppm to 166 ppm, and those are all certified value. As you can see, over the 220 days readings, the variation is typically within 10% for all those elements shown here. This demonstrates GDMS is an excellent tool for production support. So one case study we want to present is a trace sulfur analysis for nickel-based alloys. And because control sulfur level to sub ppm level in superalloys is essential to achieve the necessary performance target. And the combustion IR analysis of sulfur from high sulfur background from the flux. And there is no reference material with certified sub ppm level sulfur available for nickel-based alloy. We managed to have one standards 345A. It has around ppm level sulfur, and here shows you the SPC chart over the very long time period how we monitored. This chart demonstrates in our facility GDMS can be reliably used to monitor the sulfur level at sub ppm levels also. The second case study relates to high purity alumina. High purity alumina are manufactured in the two format, in pellets or powder. They can be used either to make the synthetic sapphires or directly used in manufacturing process. In terms of sapphire, they're used for LED and semiconductor substrate, and also making scratch-proof glass for smart devices. In terms of direct usage, they are known to be used as ceramic coatings on separators of the lithium-ion batteries, or their phosphor coatings. In all those high purity alumina, impurity affects crystal growth process, the optical clarity, the surface hardness, electrical characteristic in semiconductor materials, thermal diffusivity, dielectric constant, thermal expansion coefficient, as well as electrochemistry behaviors. So there is a need for full survey to account all those impurity atoms. There are challenges with this high purity aluminum analysis. It is difficult to digest, so solution-based technique often has a lot of problem issues. It has a memory effect if we're using graphite furnace-based technique, because alumina will react with graphite, creating a lot of roughening of the surface and hence the memory effect. In standard GDMS mode, because this is non-conductive, so it doesn't work. EAG come up with a secondary electrode technique using tantalum or indium electrode to allow this analysis happen. Here is how a tantalum electrode basically is a pin, create a groove, and from on top of it we put a solid crystal or powders pressed on it, and it allows us to do the analysis. Here shows you the GDMS full survey analysis capability for high purity alumina. It covers all the elements from lithium all the way to uranium. And most elements, the reporting limits is 0.05 ppm to 0.1 ppm. So they can easily certify 509 purity alumina. The third case studies relates to graphite and carbon forms. High purity graphite are used in many areas in the form as isostatic pressed graphite, composites, anodes, flexible graphite, or making silicon carbide directly. And these are the details of each one, including nuclear-grade graphite in semiconductor industry as wafer carriers, acceptors, single crystal crucibles. Ceramic matrix composites in anode application, it can be used as hydrogen fuel cell bipolar plates, lithium-ion battery anode, alkaline battery anode, and as for thermal management materials. In this graphite, the impurity plays multiple roles. They can be acting as a neutron absorber, electronic impurities, oxidation accelerator or inhibitors, crystal growth impurities, magnetic impurities, inclusions in engineering coatings, as well as phonon electron scattering centers. Here I give you an example how the impurities played a role in nuclear-grade graphite. Because nuclear-grade graphite is exposed in intense radiation, material can sublimate. So boron, silicon, titanium plays a role to suppress the radiation-enhanced sublimations. The second major category, of course, characterization, whether benign or deleterious. And then there is another most important category of impurities called neutron absorbent, including cadmium, samarium, and all other highlighted here. GDMS, again, provides a full survey analysis capability for high purity graphite. In general, most elements can have reporting limits from 0.01 ppm to 0.1 ppm. It can easily analyzing 5.9 to 6.9 purity graphite with the total metal impurities summarized to 4.5 ppm. Give you an example how GDMS is used for high purity graphite application is to monitoring boron levels in high purity graphite. This is a summary of the results we did over 1994 all the way to 2003, so 1 decade. We're analyzing overall about 440 lots. You can see it shows very nice control, and if there is outliers, we can spot it out. Case study 4 is dealing with trace analysis for electronic grade titanium using alternative discharging gas. Electronic grade titanium is essential for many advanced technologies. They are used for sputtering targets, tungsten toy. They are used in jet engine mid-pressure titanium aluminum vein. They are used in making the shape memory alloy natinol, as well as emerging additive manufacturing, titanium aluminum vanadium powder feedstocks. There are ASTM method and the AMS method define or specify the impurity levels needed. So basically, you can see it requires a full survey abilities to take into account all the impurities in those materials, titanium-based materials. Now, a little fresh is that why we want to do this is that GDMS is again using atomisation ionization process with high resolution mass spec to provide full periodic table coverage, direct sampling, easy of sample preparation. And this analysis is based on ASTM procedure, and we have certified reference materials and reference materials traceable to establish traceability for all the analysis. However, based on ASTM method, it is not without issues. One of the issues is that it creates argon-related molecular spectral interference for several important material elements in titanium-based material, that including calcium, scandium, strontium, yttrium, and rhodium. Here you can see when the analysis of those isotopes, like calcium 44, scandium 45, yttrium 89, and rhodium 103, it has a strong argon interference here, and it's not easy to resolve. Now, if we're using alternative gas, as here you can see the limit of detection is very high. Now, if we're using krypton as discharging gas, can we resolve the spectrum interference? The answer is yes. Now you can clearly see those mass interference are gone. As a result of it, we have successfully lowered the detection limits by a couple orders of magnitude. Here shows you the full survey analysis capability of GDMS on electronic grade titaniums. And you can see the reporting limits are from 0.1 ppb to 0.05 ppm. With krypton alternative discharging gas, those elements highlighted here have very low detection limits. Here, I give you an example that GDMS can be used very effectively for lot-to-lot quality control. Here we have 4 lots of titanium, aluminum, vanadium lots. You can see, in spite of they are producing in same manufacturing, by same manufacturer, they can experience variation in terms of type of impurities and the content levels. The final case studies we are going to discussing is the depth-specific measurement of impurities in multi-layered structures. Here we will talk about 2 modes that we're using for depth-specific measurement. The first mode is continuous DC mode. The second is microsecond pulse DC mode. All is based on fast flow GDMS technique. Why we want to do that? This focus here is on the engineering coatings. Engineering coatings are used to provide the corrosion resistance, thermal resistance, and wear resistance. So they are manufactured in many different ways: anodic coating, conversion coating, galvanized coating, electroplated coating, chemical vapor deposition, diffusion coating, PVD process, glass and enamel coatings, or demo sprayers. Of course, each of those ones have different structural characteristics, so such as residual stress, microstructure, composition, crystal structure, etc. So obviously we need to characterize them, and there are many techniques are used to do this engineering coating characterization. One of them is GDMS. It provides information on the surface treatment depths, coating thickness, composition, and most important, contaminant information in those engineering coatings. Give an example here. The first example is fast flow GDMS depth-specific measurement of bond coat nickel superalloy in continuous DC mode. Superalloy vents used in the hot zone of jet engine and the industry gas turbines generally require ceramic coating protections. A bond coat of tens of micrometers thick is applied to bond coat to bond TBC to nickel superalloy substrates. The impurity type, the concentration, and their distribution in the coating, the substrate, and the interface, particularly the latter, has fundamental impact on the coating adhesion. So the solution for that is a fast flow GDMS in continuous DC mode. This allows very deep, rapid engineering coating analysis. In any report we give you, it includes two portions. First is on the impurity levels in the bulk of the superalloys, as shown here. The second part of information we give you will be the bond coat and the nickel superalloy interface information, which will allow you to identify what kind of impurities there and where they are located. In this case, you can see there is enrichment sulfur, oxygens, from the interface of the bond coat to the nickel superalloy substrate. The second example we're dealing here is, again, using fast flow GDMS, but for depth-specific measurement of impurities in CIGS photovoltaic cell. We're using microsecond pulse DC mode. One of the challenges in CIGS PV cell is that it has multi-layer structure. It has a micron thick CIGS layer, it has sub-micron thick moly layer, and it has a steel substrate. The key information includes contaminants type, because you need to know, and the concentration and the distribution, particularly in this interface. The solution for this one is fast flow GDMS in microsecond pulse DC mode. It can achieve gentle sputtering in tens of nanometers depth, and it can survey simultaneous up to 25 elements with a sampling size 4 to 8 millimeters. Here example is this is a moly layer, and between the moly and the CIGS layer here, you can see there is accumulation zinc, as well as some nickel there, and high mobility sodium and some sulfur. In the moly steel substrate interface, and you will see the mobile ions like potassium. Okay, so you can see this capability of simultaneous surveying up to 25 elements is a very powerful tool. The third example, or the last example we are trying to show here, is ceramic matrix composites materials. You can see it has very rough surface features. The length scale of anisotropy is a few microns, a few millimeters. And here shows a detailed structures in the 50 micron scale, and you can see it's very rough. So how do you do the surface contaminant analysis of this one? It is, you don't know the contaminant level, you don't know what kind of contaminants, and it's a very rough surface, and it has a very anisotropic structure in length scales of millimeters. The solution is fast flow GDMS operating in microsecond pulse mode. This, of course, it has sampling area of 8 millimeter, which can cover not just one, but much larger features. And because GDMS has a purity survey ability, so it makes it perfect to detecting unknowns. The pulse operation can create a jet stream and pressure waves that can quickly stabilizing the signal, enabling survey analysis of known impurities. Here is the data we collected from the one of CMC, commercial CMC samples. You can see it can scan all the impurities from sub ppm level all the way to 100 ppm levels. And here is elements we demonstrated here that we know have an impact or performance impact on the CMCs. In summary, GDMS has a lot of strengths. It is full survey of 72 elements. It provides depth-specific information. It has exhibited excellent long-term precision for production support. It can reach parts per billion detection limit if it's needed. And one of the important features is it has very limited matrix effects, allowing analyzing samples without strict matrix matching standards. And it's a very robust technique as a direct solid sampling technique. Like any other technique, it has limitations. You have to deal with the sample homogeneity if it's not very homogeneous. And it has to be vacuum stable. So for organics, liquids, and matrix, you have to be very careful. And it doesn't provide the lateral resolution needed. And because it is not a high vacuum technique, so the atmospheric species like hydrogen, carbon, oxygen, nitrogen need to be very careful. But EAG does have a complementary technique for each of those aspects. We have a solution ICP-OES MS technique, we have laser ablation technique, and we have IJ technique to address those challenges. Overall, GDMS is a successful story. It is based on international test standards and the rapid turnaround. We have served many industries shown here. So why we're choosing EAG? Number one, client confidentiality is core to our business. We are established thought leaders in investigative science. We have extensive knowledge based and skilled expertise. We often take the multidisciplinary approach, and we can scale with your demand to meet your time constraint. We serve we have over 2,500 instruments to provide to meet those needs. And we are a global leader for material testing services.